All right, in today's lecture, we're going to cover the section 5.6 material on some applications of multiple integrals. So throughout chapter 5, we've defined double and triple integrals of functions of 2 or 3 variables over different plane regions or regions in space, and saw that for some regions, we can evaluate these double or triple integrals more easily by making use of polar, cylindrical, or spherical coordinates. So in this last section for our Chapter 5 material, we'll talk about some applications of these multiple integrals. Now, in this section, we're going to consider some physical applications, such as finding, for instance, the mass or center of mass of a plane region or a solid region in space, finding the total electrical charge over some plane region or a solid region. And here I mentioned we would talk about moments of inertia. We will not consider moments of inertia in this course. So the first thing that we're going to talk about in this section is how to find the total electrical charge over a plane region or a solid region. So here, let's start by supposing that we have some electrical charge which is distributed over a plane region, some region D in the xy plane, and that the charge density at any point xy in that plane, region D, is given by a function sigma of x and y. So if we have some, say, metal plate, which is having an electrical charge distributed maybe unevenly over that plate, so we have a larger charge density at certain points on our plate than other points, how could we determine the total charge over that region D? So this theorem says that the total charge would be found by evaluating the double integral of that charge density function, sigma, over our plane region D. And here we're using capital Q to denote that total charge. So let's look at an example of finding total electrical charge over some plate. So here we are told the electrical charge is distributed over the unit disk, that is the disk of radius 1 centered at the origin, and the charge density at any point xy is given by this density function, sigma, which is 1 plus x squared plus y squared, measured here in coulombs per square meter. And we are asked to find the total charge over this disk. So let's visualize it really quickly. We have some circular plate in the xy plane, which is described by the unit disk, so that is the disk of radius 1 centered at the origin. And this is our region D. And over this disk, the electrical charge density is given by 1 plus x squared plus y squared. So notice here, the larger that x or y are, the larger x squared plus y squared is. So we have a larger density for electrical charge on the outside or towards the outside of our disk. And then at the inside of our disk, at the point 0, 0, our charge density is 1. As we move outward from that center, we get a larger charge density here. And the question is, well, what is the total electrical charge over this disk? So to find that total electrical charge, we can use our new theorem on finding electrical charge, which says that we would evaluate the double integral over this disk of our density function, 1 plus x squared plus y squared, with respect to A. Now, because of the shape of our region, since it is a disk, we would likely want to use polar coordinates to set this up as an iterated integral instead of rectangular coordinates. So here, our disk D could be described as the set of points whose polar coordinates are theta, are given by r ranging from 0 to 1, since we had a disk of radius 1, and theta would range from 0 to 2 pi, since we're considering the full disk. That is a full rotation around our circle. So, using polar coordinates, the total charge q, setting up an iterated integral, would be given by the integral from 0 to 2 pi for theta and from 0 to 1 for r. And then changing our integrand to polar coordinates, we have 1 plus x squared plus y squared, which is r squared. And now the differential of area in terms of polar coordinates is given by r dr d theta. So here we notice that our inner integral with respect to r is a constant in terms of theta. So I could pull this out in front of my theta integral, and then integrating a constant with respect to theta on the interval from 0 to 2 pi gives us the length of that interval, which is 2 pi times the constant, which was the integral from 0 to 1 of, if we distribute our r, we have r plus r cubed dr. So we are left with 2 pi times, for our antiderivative, we have 1/2 r squared plus 1/4 r to the 4th, evaluating from 0 to 1. So we have 2 pi times 1/2 plus 1/4. When we plug in 1, subtracting what we get when we plug in 0, we are left with 2 pi times 3/4, or 3 pi over 2. Now here, our unit, we were measuring the charge density in coulombs per square meter. Since we were integrating over a plane region, our area unit was in terms of square meters, so the unit we're left with for this double integral is coulombs. Okay. Let's look at some other types of problems. Now for this example, we were considering total electrical charge over some plane region. If we were interested in electrical charge over a region in space, we would need to know the density function in terms of x, y, and z. So in space, if we had the same sort of problem, we would evaluate the triple integral over our region of space where our charge is distributed, and we would integrate whatever the charge density function was in space, sigma of, say, x, y, and z with respect to volume. So we could extend this to find total electrical charge over a solid region in space. So let's look at some other types of problems. This next problem that we'll consider is a problem that you looked at in Calculus 2. Here we'll look at another way to solve this sort of problem. So here we are going to consider some flat plate, or a plate of very, very thin width, which is sometimes called a lamina, that occupies some region D in the XY plane. So maybe it's some plate of an odd shape, but a very odd shape, but we could think about this shape as being bounded by curves or occupying some region of the XY plane. And let's suppose that the density of this lamina at a point xy is given by rho of xy, where rho is some continuous function on our region describing the lamina. So maybe this plate is made out of some material that has non-constant density. Maybe it's more dense or more stiff in certain parts of this plane region. So the question would be, how could I determine the center of mass for that lamina? So if I were to try to balance my plate on a pinpoint, where do I need to place that pin so that this lamina would be balanced? What is its center of mass? So here, let's consider that problem. Let's suppose that we have a lamina occupying a plane region D in the xy plane, and it has a density function rho of xy at any point. So we could define the total mass of that lamina as the double integral of the density function over that region D. So we would add up its density at each point throughout that plane region in order to find the total mass. And then to find the center of mass, to get our center of mass here, x bar, y bar, some point in the plane, we would use the following equations. To find the x-coordinate for the center of mass, we take 1 over the mass of our lamina times the double integral of x times our density function over the region D. And to find the y-coordinate for the center of mass, we take 1 over the mass times the double integral of y times the density function over our region. So now that we have this formula for finding the center of mass for a lamina, let's look at an example. So here we are asked to find the mass or the center of mass for some lamina occupying a region D, which is the region in the first quadrant bounded by the parabola y equals x squared and the line y equals 4 that has a density function given by x times y. So let's start by visualizing our plane region here. So we're talking about the region in the first quadrant of the xy plane, which was bounded by the parabola y equals x squared. So that is the parabola whose vertex is at the origin opening upward, and the line y equals 4, which is the horizontal line passing through y equals 4. So we're talking about this shaded region. So when y equals 4 here, x would have to be 2 since y was equal to x squared, and we had our vertex at the origin. So we have some plate that occupies this region. It has this shape, and the density function is given by rho equals x times y. So the larger that we make x or y, the more dense this plate becomes. So it's more dense moving outward from the origin than it is at points towards the origin. So if we're interested in finding the center of mass or the mass of this object, we can make use of a double integral. So first part of the problem asks us to find the mass. So here, the mass of our object M is found by taking the double integral over our plane region D of the density function, which is x times y with respect to area. So here, setting this up as an iterated integral, well, our region D we can think of as a type 1 or type 2 region. So here I might think about this as a type 2 region to make the integral a little bit easier to evaluate. So if I were to integrate in the order dx dy, my outer integral with respect to y, well, y can range between the constant values 0 and 4, and then x could range from 0, that is this positive y-axis, and it could move outward to this parabolic arc, which was defined by y equal x squared, or solving for x, x is the square root of y. So we would go from 0 to 4 and 0 to root y. We're integrating x times y in the order dx dy. So let's see what we get here. We would have, for our inner integral with respect to x, the antiderivative would be x squared over 2 times y, evaluating from 0 to square root y, and then integrating with respect to y. So if we substitute the square root of y in place of x, we have the integral from 0 to 4 of y squared over 2 dy. So for our antiderivative, we would have 1/6 y cubed, or y cubed over 6, evaluated from 0 to 4. And so we find that our mass is given by 4 cubed, which is 64 over 6, or simplifying 32 over 3. So this would be our value for the mass. Now, in order to find the center of mass, we're going to use the formula that we had for x bar or y bar. So let's start by finding x bar. To get the x coordinate for our center of mass, we take 1 over the mass, so in this case 3 over 32, times the double integral over our region of x times the density function, which was x times y with respect to area. So let's set this up as an iterated integral. So here we have 3 over 32, expressing d again as a type 2 plane region. We could integrate from 0 to 4, and then from 0 to root y. Our function is now x squared times y in the order dx dy. So let's see what we have here. Our antiderivative with respect to x gives us a 1/3 x cubed. Now if I pull the 1/3 out in front of my integral, I'm left with 1 over 32. The integral from 0 to 4 of x cubed times y from 0 to root y dy. So let's see what we have. This is 1 over 32 times the integral from 0 to 4 of, substituting square root of y, or y to the 1/2, in place of x, I would have y to the 3/2 times y to the first, which leaves me y to the 5/2 power dy. So let's see what we get. We've got a 1 over 32 times the antiderivative of y to the 5/2 would be 2 over 7 y to the 7/2, evaluating from 0 to 4. So plugging in 4 in place of y, well, 4 to the 7/2 is the same as 4 to the 1/2, and then raised to the 7th. So 4 to the 1/2 would be root 4, or 2, raised to the 7th power, then times our other 2, and then with the 1 over 32, 1 over 7, this reduces to 128 over 112, or we could simplify a little bit. So this would be our x coordinate for the center of mass. And to get our y coordinate for the center of mass, we would again take 1 over the mass, which is 3 over 32, times the double integral over d of y times the density function xy. So let's see what we have here. We have 3 over 32, and setting this up as an iterated integral, we could go from 0 to 4 along the y-axis, and x is bounded by 0 or root y. The integrand is now x times y squared in the order dx dy. So let's see what we have. Antiderivative with respect to x first would give us a 1/2 x squared, or if I pull my constant 1/2 out in front, we have 3 over 64, integral from 0 to 4 of x squared y squared from 0 to root y dy. So plugging in the square root of y in place of x, here we have 3 over 64, integral from 0 to 4 of, y cubed dy. So for our antiderivative, we have our 3 over 64 times y to the 4th over 4, evaluated from 0 to 4. So plugging in 4 for y, we have 4 to the 4th divided by 4, or 4 cubed, which is 64, times 3 over 64 leaves us with 3. So here, for these center of mass problems, it's helpful to sketch your region because you can kind of check your answer at the end, or at least make sure it seems reasonable. So here, our center of mass, we want to make sure lies within our region and seems to be at a reasonable point. So here we found x bar was 128 over 112, so something a little greater than 1. And our y coordinate was 3. So we have a center of mass that lies somewhere right here. So that seems to be reasonable. It lies within our plane region, and it lies a little more towards the upper right-hand side of this region, since the density function was x times y. So remember, this thing is more dense towards the upper right portion. So that center of mass would be a little more skewed towards the upper right part of that plane region. All right. So let's look at some other problems. In the next part of this section, we'll extend the concept that we just talked about to finding the center of mass or mass of a solid region. So here we will look at the mass or center of mass for a solid. So let's suppose that we have a solid region in space, occupying a region, E in space, and it has variable density throughout. Its density function in 3 dimensions or in space is given by rho of x, y, z. Then the total mass of our solid would be found by evaluating the triple integral of that density function over the solid region E. And the center of mass, which would be a point in space, x bar, y bar, z bar, is found by evaluating the following triple integrals. So to get x bar, we would evaluate the triple integral of x times our density function over the region E, and then divide by our mass n. Similarly, to get y bar, we would have 1 over the mass times the triple integral of y times our density function. And to get z bar, we would take 1 over the mass times the triple integral of z times our density function. So let's look at an example of such a problem. So here we are considering a solid region E, which is bounded by some surfaces, the first of which is a parabolic cylinder, z equals 1 minus y squared. Here the variable x is missing, so it's extending along the x-axis, a cylinder along the x-axis. And its cross-sections are parabolas. So it's like z is 1 minus y squared. So our cross-sections here with fixed values of x look like downward opening parabolas with vertex at y equals 0, z equals 1, and decreasing or opening downward. Then we are also considering our solid as being bounded by the planes x is equal to, or x plus 5z is equal to 5. So that is this plane shown here, which of course intersects our parabolic cylinder in a little parabolic arc. And the plane x equals 0, so that is the yz plane. So here when x equals 0, we have this yz plane, looks something like this. And then the plane z equals 0, which would be the xy plane. That is our plane down here in the bottom portion of our figure. So let's see if we can describe or highlight the region that we're talking about. So it's bounded by the YZ plane, this plane, the XY plane, and our parabolic cylinder here. So we have this region shown here that is our region of interest, front edge. So a little bit hard to visualize, that's why we've included the graph here. And we are asked to find the mass of that solid, where here this solid is said to have constant density throughout density 2. So let's think about how we would evaluate the mass. We need to take the triple integral of our density function, which is 2, over this solid region. So we need to think about how to describe this region as type 1, 2, or 3. So let's start by describing this here. We can think about E as consisting of the set of all points x, y, z, such that x is bounded below by this YZ plane. So that is the plane x equals 0. And it's bounded above, in our x direction, by this plane where x plus 5z is equal to 5. So solving that for x, we would have 5 minus 5z. And then if we project this solid onto the YZ plane, that is the plane where x is equal to 0, we have a plane region in the YZ plane, which looks like a region bounded by this downward opening parabola. If we slice our region, which is bounded on the edge by this parabolic cylinder, we have the following plane region D. So here it had a vertex at 1. Our intercepts would be plus minus 1 for y, since z was 1 minus y squared. So here we could bound z below by the y-axis, which is z equals 0, and above by the parabola 1 minus y squared, where our y values could range from -1 to +1. So a little bit tricky to describe this region. And so to find our mass for this region, we would evaluate the triple integral over E of the density function, which is a constant 2 with respect to volume. So setting this up as a triple integral, we have our outer integral would be with respect to y from -1 to 1. Then with respect to z from 0 to 1 minus y squared. And with respect to x from 0 to the plane 5 minus 5z. All right. So our function was 2 in the order dx, dz, dy. So let's evaluate this. So our inner integral is of a constant 2 with respect to x over the interval 0 to 5 minus 5z. So integrating any constant over an interval of a given length gives us that constant times the length of the interval, which in this case would be 5 minus 5z minus 0. So just 5 minus 5z, then integrating in the order dz, dy. So here we could first distribute our constant 2, and we have 10 minus 10z dz dy. So our antiderivative with respect to z, let's see what we have. We have 10z minus 5z squared, which is being evaluated from 0 to 1 minus y squared dy. So let's see what we get. When we substitute this in, we have the integral from -1 to 1 of 10 times 1 minus y squared minus 5 times 1 minus y squared quantity squared minus 0, and then integrating with respect to y. So to evaluate this, we could expand, and let's see what we have. We've got the integral from -1 to 1 of, distributing our 10 to the first term, we have 10 minus 10y squared, and then we are subtracting 5 times, if we expand 1 minus y squared quantity squared, we have 1 minus 2y squared plus y to the fourth dy. So expanding and grouping like terms, let's see what we're left with. We have the integral from -1 to 1 of, grouping our constant terms, let's see what we have. So we had a 10 minus 5, so that leaves us a constant 5. Grouping our y squared terms, we had -10y squared minus 5 times -2 would be plus 10y squared, so those terms cancel. And then we're left with our last term, this minus 5 times y to the fourth, so minus 5y to the fourth dy. So our antiderivative with respect to y gives us 5y minus y to the fifth from -1 to 1. So evaluating at 1, we have 5 minus 1, which is 4, minus evaluating at -1, we have -5 plus 1, so subtracting a -4 leaves us with 8 for the mass of this solid. And then we were also asked, or as I say here, continued on the next page, the next part of this question asks us to set up but do not evaluate integral expressions to find the center of mass for this solid. So let's think about how to set up our integrals for the center of mass. To get x bar, we would take 1 over the mass, so 1/8 of the triple integral over the solid E of x times my density function, which is 2 with respect to volume. So here, if we want, we can pull our constant 2 out in front. I would have 1/4 of the triple integral over E of x dv. So if I wanted, I could set it up as an iterated integral. We've got 1/4 integral with respect to y was from -1 to 1. With respect to z was from 0 to 1 minus y squared. And with respect to x was from 0 up to 5 minus 5z. Here we're integrating x in the order dx, dz, dy. So here we're asked to set up this integral but do not evaluate it. So here we would have our integral expression. If you're curious, if you evaluate this, this works out to 5/2. Now for y bar, we would have 1 over the mass times the triple integral over the solid region E of y times our density, which was 2 dv. So again, pulling out the constant 2, we would have 1/4 of the triple integral over the solid E of y dv. So here, again, as an iterated integral, we would have 1/4 from -1 to 1 from 0 to 1 minus y squared, and from 0 to 5 minus 5z. We're integrating y in the order dx, dz, dy. So you can check if you evaluate this. This works out to 0, but we are just asked here to set up that integral. And our last coordinate for the center of mass, z bar, is given by 1 over the mass, so 1/8, times the triple integral over the region E of z times our density function, which was 2. So in a similar way, we have 1/4 the triple integral over E of z dv, or setting it up as a iterated integral, 1/8 integral from -1 to 1, 0 to 1 minus y squared, and 0 to 5 minus 5z. We're integrating z, or excuse me, I had a 1/4 constant out here for this last one after we simplified. We're integrating z in the order dx, dz, dy. And if you evaluate this, you can verify you find this is 2/7. But again, here we're just asked to set up this integral for that coordinate, not actually to find it. So we can see from this last example, well, it's possible to find the total mass or center of mass for a solid region of varying density, but it can get a little tedious as we have to evaluate a triple integral to find any coordinate for our center of mass or the mass itself. So I guarantee I would never ask you a question where you had to find all 3 coordinates for the center of mass. I could ask you maybe something like part A, find the mass, where you only have to evaluate 1 triple integral, but it's sort of overkill to try to find the coordinates for the center of mass in any sort of short time frame.